Image warping is an editing technique with broad utility in photography and special effects. We have developed a new method for computing image deformations that combines speed with accuracy. Our method leverages a custom elastic membrane model and an efficient grid-based discretization of the deformation field. We allow for user-imposed constraints to be resolved at subgrid accuracy without the need for remeshing. Our regular discretization facilitates the use of a highly efficient multi-grid solver for computing the deformed image shape. One of our contributions is the ability to impose displacement constraints along arbitrary spline curves, which do not have to be aligned with nodes on the regular Cartesian lattice used in our discretization. For example, accurate closing of the mouth is enabled by precisely targeted curves designed to move the lip upwards while keeping the teeth in place. This example edits a hand pose by separating some fingers and bringing others closer together. Zooming into the details of the warped grid, we observe that our elastic membrane model is able to stretch to create separation, compress when image contraction is desired, and bulge to approximate area preservation when no constraint dictates otherwise. Our novel energy density function facilitates squash and stretch behavior, as demonstrated by the exaggerated deformation of a boxer's face. Woody demonstrates that our method works well with even sharp, non-smooth target curves. Here we show a warp of an image of a toy figure where we force the arm of the figure to articulate in a different pose than photographed. Another application of our method is image morphing. Here we demonstrate a smooth transition between two faces. Our method accommodates the preservation of image area when such behavior is desired. Such properties can be specified in a spatially varying manner, for example, by a grayscale image mask that designates certain image areas as more incompressible than others, as shown in the sponge example. Stretching this object intuitively results in a narrowing of the midsection, as image area is preserved. This next example illustrates the spherical object being pinched between two fingers. This first video illustrates how a commercial morphing application would handle two spline constraints that bring the tips of the fingers closer together. Instead, our technique can produce an area preserving effect, forcing a pinched sphere to balloon out on either side to preserve area. Of course, it would be possible to explicitly constrain the final shape of the sphere, but this would require manual intervention with several additional constraints. This next example illustrates the robustness of our method to large rotational motions. Our method is able to produce this 90-degree swirl without folding or inversion. This is an example of where alternative techniques could easily fall victim to image folding, as demonstrated in this deformation produced by a production quality morphing tool. This example presents a visual illustration of one of the limitations of our technique. In situations where area preservation has been prescribed, we can sometimes get unintended consequences if we do not provide a spatially varying compressibility mask. In this pinch example, we do not specify which areas of the image should be preferably incompressible, making the entire image resist compression uniformly. As a consequence, the unintended incompressibility of the gap between the sphere and the rest of the hand forces the finger to thin out in an unrealistic fashion. A key advantage of our regular grid-based discretization is that it enables a very efficient multi-grid solver for the numerical solution of the membrane deformation problem. Even for modest resolution, our multi-grid solver converges much faster than iterative Krylov subspace methods, with only a fraction of the cost. We compare our method to the extreme image deformation presented in the locally injective mappings, or LIM, paper. In contrast to LIM, our method does not avoid inversion during the course of the iteration. However, at the end, all elements successfully recover from inversion and produce a fold-over free result.